Интерактивные мероприятия, говорите? Будущее покажет. Добро пожаловать на виртуальный саммит.
Awesome, great. So I'm Mohamad Mokbel. I work for Trend Micro, and today I'll be talking about my own exploratory endeavor in the reverse engineering of a multi-platform compiler, and in particular, pure basic compiler. Although I hope that the talk is not like the end message of the talk is not just specific to pure basic as much as about the actual process behind it that I went through to reverse engineer this compiler. And as you can tell from the title, it's an exploratory endeavor, meaning that I have to go right, left to get what I want and to piece different things to make sense of what I'm trying to do, just like when Columbus discovered America. So there's no set path that you have to take to get what you want. So this is the this is the process there. So yeah, a bit about me. I know a lot of you don't know me. So I'm a senior security researcher at Trend Micro. I'm a member of the Digital Vaccine Lab, and my interest lies in the areas of reverse engineering, malware, IDSs, intrusion detection systems, intrusion prevention systems. I'm very fond of the C++ programming language and compilers, and a bit on the software performance analysis side on different architectures. And I have a special interest in exotic communication protocols, especially protocols that don't fit particular specifications. For introduction,
reversing native programming languages versus interpreted languages and the difficulties between them. So when reversing a native programming language, you would have to think about compilers, differences in the compilers, optimizations, libraries used, processes, phases, different file format, code generation, dependencies on any particular OS. So yeah, and for malware, mostly it is written in native programming languages, in particular x86, whether it's a 32-bit or 64-bit. Then you have C++, Objective-C, or Delphi. And all of these, they inherit different runtime libraries that you have to think about when reverse engineering them. And you have to have a better understanding of how the compiler linked each of these libraries, whether it's statically linked or dynamically linked. Now, of particular, we have the Go programming language. And if you remember at the time when it was introduced, it wasn't that easy to reverse engineer, although it is a native programming language and it has a lot of metadata that it gets pushed to the executable just due to the nature of how Go compiler works. But it was still very hard to reverse engineer until Tim Strazzari released his IDA plugin, and then this is followed by Juan Calvé, who released a set of Python plugins for the Android decompiler, and this was actually pretty good work, very, very solid work. And the reason that works, why those plugins are able to give us a lot of metadata for Go binaries when reverse engineering them, is that it's just that some runtime information has to exist in the compiled binary for the program to run. So that's that for native versus interpreted languages. So this talk is not about interpreted languages in any form or shape. It's about pure basic, which we'll delve into later on. So the talk layout is, first we'll introduce pure basic, the language, a bit of examples, actually it's just one example, and then we go into the compilers and libraries. And then the thesis of the talk is literally, reversing proprietary file formats without doing any actual reversing, except in specific cases. And the talk is geared toward the Windows version of the compiler. And then we'll do like highlight 2 case studies and demo a parser that I wrote and another plugin that helps in reversing the pure basic binaries. So we start. So pure basic, it produces native code for Windows, macOS, and Linux platform. Again, it's literally native code. You can look at it. It's not intermediate or any interpreted language. Because if you Google it and see people like talking about this particular topic, there's a lot of misconception around like this particular area, which I don't know why. And then this language has an extensive library support, and you would be surprised how much it has to offer, from audio to gaming to databases to networking to writing GUI software. And it's extremely easy and like very, very, very powerful at the same time. It's I think it's probably like one-man type product. And it's a very high-level language. If you've ever used or written a program in Delphi, you will feel at home with this language. And it has support for inline assembly, surprisingly, for both 32 and 64-bit architecture. And if you've ever used Microsoft Visual Studio, I mean, the 64-bit version of the compiler doesn't even allow you to use inline assembly, whereas this unknown pure basic compiler allows you to do that. And for assembly, it uses the FASM assemblers on Windows and Linux, and YASM on OS X. You can actually use pointers for memory access. It does give you such low-level access. And if you want to call into any of the shared native libraries on your preferred OS, you can do so via these helper functions called call function and call C function, depending on the calling convention. And some of the features of the language itself is, of course, you can use procedures, meaning functions, structures, interfaces. If we're talking about C++ or Java, it's adjusted classes with basic inheritance, just like one-level inheritance. And in this language, they are known as extends, not inheritance, like not inherit or anything like that. So yeah, so this is an introductory example about how you would write a program in this language. So if you want to define a structure, this is how you define it. So in this case, we have a structure named COVID-19, and it has these 6 data members. And the way you define or give a type for a given data member is by ending the name with a dot versus and followed by the type, or just like one letter. In this case, name would have the type string, dead the type bool, date infected type string, age type integer, and whatnot. If you want to have a data member with a type float, it would be .f. And then we create a list of that type, a list named patients of type COVID-19. And if you want to add an element to that list, you would have to use the add element API. Now, if we want to populate these data members, this is how you do it. First, the name of the list, open parentheses, followed by backslash, followed by the data member that you want to access, and then you give it the name. By the way, this is a fictional character. I just came up with this name, so don't just go about Googling and hoping that you would find this particular person. And if you sort of like get tired of repeating the name of the element, I mean like patients, you can just use the this unique construct called with and end with. And so if you say with patients, and then you can just reference the data members without having to type the list name every time you populate a given data member. So after that, let's say we want to pop up a message with some specific information from this data structure. We use the message requester. But prior to that, let's say we have multiple elements in this list. You got to select a particular element with the index. In this case, we use the select element or the index, or I should say the element in that list that is 0 in this case. So we only have one element in it. And then in this case, we call message requester printing out a dialog box with the title and the body of the message and the constant at the end, which is just an OK body. And if you want to clear the structure, use the clear structure API. And this is how this dialog box just shows what libraries in pure basic some of these functions reference. For example, clear structure is coming from a library known as memory, and the element one pertaining to the list, they are coming from a library called linked list. And for message requester, it is from the requester library. And since we are building this, let's say on Windows, so if you want to do a bit of deep dive into this, you will see that message requester at the end of the day calls message box Windows API. So after you run this is what you get. Just the typical dialog box on Windows. Now we're going into the compilation components of this particular compiler. So if you go like after installation and you go to the composite directory, this is what you see. So first we have the phasm.exe executable. This is an open source flat assembler for x86 processors. It's an assembly engine. It's very powerful and has a macro instruction language. I'm pretty sure most of you, whoever did reversing or wrote any assembly, must know how easy it is to use this assembler. And the compiler, every time you use it to like link the final object file, it always produces, like for whatever program, it produces an object file under this particular name, purebasic.obj. And it is in COF format, common object file format. So for linking, the compiler uses polling, which again, another open source linker for linking multiple object files that's generated by this compiler. And then it comes with Polid, which is just a library manager, which is again an open source by Bell. And you can use it to build import libraries, extract object files, or delete or list them or whatnot. Actually, at some point in time, I didn't realize that this executable exists, and I was planning to do it like write this thing from scratch myself, but then hopefully I found it before. And then we have this another open source from Bell tool called the resource compiler, which is used for creating resource file, but like resource file they are used for hosting the, for example, DB elements or any of these stuff. And comes the orchestrator, the master of all of these things, the PB compiler. So this is the main compiler. This is the actual component that actually emits the phasm assembly instructions. And it's always written under this particular file name, purebasic.as. So these are fixed. So as stated, it is orchestrated that leads to the generation of the final executable. So as you can tell, the guy is actually quite smart. He didn't have to implement any of the back-end components of the compiler as much as just the front end, as we'll see later on in the next slide. So this is a very smart move on the author of this compiler. It makes his life very easy by leveraging other people's work and focusing only on the front end sort of component, front end / next end, which is called like intermediate type end. So if we to follow like the process of compilation of this compiler, it goes like this. So let's say we have this example, and the extension for the file is .pb. So, and all it does is it just uses the message requester API with the title hello, the text word, and it uses the constant message requester OK. So this is the pure basic source code translation unit that you feed into the compiler, PB compiler, which does the lexical analysis, syntax analysis, and the code generation. So this compiler leads to the generation of the actual phasm assembly code under the name pure basic.as. And here in this extremely and heavily truncated assembly snippet, you can see the nature of the generated assembly code. And it's very readable. And like here, I'm omitting the prologue of this assembly snippet. But you can test it yourself and you see the whole code. And then you use phasm to generate the object file. And then you want to link the object file to generate the final exe file. The compiler would use the PORC or polling executables. So this is the whole process of how the compiler goes about generating an actual executable file. The process would be it should be very similar on Windows and Linux, but just that use a different assembler. Moving forward, so this is like a more of a dynamic example of how the compiler would, like at the command line, how it would sort of like piece all these commands together for generating the final executable by calling the polling executable and giving it all these parameters that are, or at least I hope they are sort of explanatory. So I won't go in depth into each one of them. Now, the libraries, which is the crust of this talk, because they are stored in a proprietary file format, and they are different from Windows versus Linux and macOS. So on Windows, they are stored zlib compressed with a particular header, so that the compiler can use them whichever way they want. Whereas on Linux and macOS, they are stored encrypted. Now, why? Of course, there's a reason for that. Actually, the author of the compiler doesn't want you to have access to these libraries that have all this rich functionality that you can use with your own program, because they have all the export APIs for you that you can just call and to perform whatever function you want. So the compiler is shipped with different types of libraries. So if you go under the compilers directory, you will see that you have this set of libraries. Like, for example, debugger. If you want to debug your program, so this library would be referenced. If you want to use a database type code, then you see the libmaria DB, and the list goes on. And now we have the list of pure libraries. So under this directory, we have around 116 libraries, and this is the this is where all of the functionality of the compiler resides. It's in this particular folder. If you want to send an email and you're calling any of the functions of this library, it is in a library under the file name mail. And if you want to write an FTP client, it's under a library called FTP, and the list goes on. And by the way, just so you know, all of this work is specific to version 5.71 of the Pure Basic compiler. This is at the time when I started working on it. Now I think they have 5.72, but nothing major has changed. It's still a minor release. And now if you go to, if you're on Windows, so you have this directory, Pure Libraries, Windows Libraries, where you have some of the Windows proxy libraries. And if you want to write your own library, this is where it resides. It's under this particular directory. The compiler comes with its own SDK, where you can write your own library and use it in your code. Now, this is actually quite an interesting design decision from the author perspective, and I found it quite good, actually. So it has these two different subsystems. So, for example, when you want to write like OpenGL or DirectX 11 code, you don't need to use specific APIs for each of these libraries. If you have a higher level API that would call into each of these libraries. And the way to decide on which subsystem to use is at the time of compilation, you just reference a specific subsystem, which is a very good design decision when writing compiler or software engineering any particular software. Now on Linux, you have GTK2 and Qt. Yes, and then another interesting design decision is what's known as residence. And these are precompiled binary files, and they are used for storing like predefined structures, constants, interfaces, and macros. And this is, again, a very good decision because it makes it easier to load all of these at once, even like before compilation, just at the time when you run the compiler. So usually like on when you use C++, you would have to include the header file, right? And you know the struggle when you have to deal with this, when you have multiple object files and you have to deal with all the different references, and so you end up with collisions and multiple inclusions. So this is a very good design decision. And if you choose to write your own resident files, the compiler actually comes with this functionality via the option create resident. Or if you want to peek into some of these resident files, the compiler IDE comes with a built-in structure, a viewer GUI tool. So you don't have to write your own tool. At one point in time, I decided I wanted to write my own tool until I stumbled on this already written tool by the author. I know now you might be wondering, so why all of this? What is the purpose of this talk? I hope you already read the abstract and things become clearer. So since the goal of all of this is that when you want to reverse engineer a native binary, as I mentioned at the beginning on the difference between native and intermediate languages, is that for native, you're going to have to account for all the runtime libraries, whether they are statically linked or dynamically linked. So when you reverse engineering them with your favorite tool, be it IDA or Giga or any other tool, it's easier if you have, for example, a flirt database in IDA, flirt signature, that would auto-annotate these already known functions for you, right? So, for example, for Visual Studio, for Delphi, already IDA comes shipped with these flirt signatures, thus you don't notice it. So for this particular compiler, this is what it's trying to do, is to get a hold of these particular libraries and generate our own flirt signatures for IDA, so that reverse engineering pure basic compilers come easier. However, these libraries, they are, as I mentioned, they are stored in a proprietary file format, and for other platforms, they are stored encrypted. So there are different ways of approaching the acquisition of these libraries. Some of them is easy, but requires more manual work. The other one is more automated, and hopefully it is the right way, which what this whole talk is about. To start with this, so when compiling a PP program, the compiler actually, depending on what APIs you're calling, that references a particular library from the pure libraries directory, it actually extracts those libraries from their proprietary file format and saves them in the user temporary directory under this particular folder name, pure basic, followed by a get the count decimal value. So this folder always gets created, and all the required libraries for the program you're compiling are written inside this folder in their plain format. So you don't need to do any reversing or anything. And it has this format that is .lib. And then if you want to get access to the actual object file that it creates, also, as I mentioned at the beginning, it's always created under the main pure basic.obj, and the rest of the stuff, the source file, the resident file, or the manifest file, they're all under the same directory. However, and this is the point that you have to keep in mind, these files they are written dynamically, and then they get deleted right after compilation is finished, so you don't have access to them. So at the beginning, I didn't know that. It's only because I was talking with this thing, and then I said, okay, let me run procmon from system terminal utility and see what's happening on the system during the compilation process. And this is how I got to know that the program writes these libraries into this particular folder in their original format. So there are a couple of ways of how you would approach this to get access to all of these libraries in their original format. One way would be to pass the actual PD compiler and trying to find the code that is responsible for dumping these libraries to this directory, and then knopping out the code that's responsible for deleting them right after compilation or whatnot. So I did that. That was cool. But again, to trigger all the libraries, I would have to use all the code necessary that would call into every single one of these libraries. And I would have to repeat this for every release of the compiler on every platform. So this is definitely a non-sustainable solution. Thus, why I automated the whole process in a static, more rigorous way. So yeah. Now we come into the crust of the talk, that is reversing pure basic libraries proprietary file format without actually doing reversing. Only one necessary. So, as I mentioned, these libraries, they are stored in a unique way. And we'll start, I know this slide is a bit overwhelming, but we'll go through it step by step, starting with number 1 here on my left side. At the top, you will see this hexadecimal snippet. So I'm only accounting for these bytes. However, when you reverse engineer binary formats, you have to account for the entirety of the file that you look at, not just the first 10 or 20 bytes. And then this is part of the lessons learned at the end of the talk. So what I want you to get out of this is that you should learn a bit about how I approach it, as much as, so this means that, or this means this. Otherwise, you won't get the full picture of this research. So first, we see, after opening it in hex editor, in this case, I use 010 editor, my favorite hex editor. So you'll see this particular ASCII string that's streaming out at you, and it is called ERUP, right? So this is stored in Little Endian. If you reverse it, it's pure, and I'm already dealing with a pure basic compiler, so this gives me an indication this is a magic value. So that's how I start, by creating my own high-level structure. So in this case, number 1, I named this header pblib. Okay, so this is the library header. And then followed by this double word value. In this particular example, we're talking about a library named alpha image. It could be another library. It's just for illustration purposes. So the next double word value is what I call the index into the library data. Like, this is where the actual full library is stored, zlib compressed or not compressed. Okay, and this index, you're gonna have to start reversing it, starting on offset 0c. So you might ask, how did you figure that out without actually performing any reverse engineering? Again, I said this is an exploratory endeavor, meaning that I tried this, I tried that, until things start to make sense to me. So yeah, it's literally sort of like use the divide and conquer type approach until things start to make sense to you. And then followed by the next double word value, starting on offset 08. So what is this? Oh, it's an ASCII value. It's 4 build starting Little Endian, which indicates the library version. So after doing like a string dump of the compiler, you get to see that, oh, it has actually 2 library versions, 3 or 4. And then followed by this another double word value in blue. And this actually takes either of the values, 0 or 1. And this indicates that if it is 0, this means that the library is actually stored non-zlib decompressed. If it is 1, it is stored zlib compressed. So, but how do I know that it is zlib compressed if I didn't do any reversing? You will see later on how. And then followed by this double word value at offset 10. And this offset holds the size of the stored library, of the actual real library in this proprietary file format. So yeah, so this is the size of the library decompressed, as shown here in this data member. And then after that, we have the, here it's stated clearly, it's an alpha image string. In this case, this is the actual original file name of the library we're dealing with. So you could, technically speaking, you could have the library named under, like the proprietary file library under. So the first, let's say 20 by 20, no, the first 31 bytes are represented in this number 1 structure, pd_lib. So how would you know that this is the end of the file name? Well, you have the non-terminating character, since we're dealing with a string. And then followed by, now we start with number 2 structure. Now here where it gets a bit messy, but I hope I will be able to explain it very clearly. This is what I call library types, based on my investigation by looking at most of the libraries shipped with this compiler. It turns out we have 2 library types. At least this is what I call them. They need to not be called this way. So starting where we left it from, at offset 32 decimal, we have this value 01. Turns out to be it's fixed, and it's always 0, 1 for all the libraries. Okay, fine. So we won't have to do anything with this one. Now, what follows is what I call a sort of like a dynamic interpretation for deciding whether you're dealing with a library of type 1 or a library of type 2. If the byte at offset 20 hex is 0, then the next byte has to be 2. And this means we are dealing with a library of type 1. On the other hand, if the next byte is not 0, then the constant byte, the next byte, is not set. It will not be 2, meaning we're dealing with library of type 2. Now you will see later on what type 1 is and what type 2 is, the difference between them. So as I mentioned, if the offset at offset 20 hex is 0, it has to be followed by the lib type constant that I remember that is always 2. Now I have, like in this particular structure, and this is literally how I have it hard coded in the code in my parser. I have these what I call shadow members because they are not part of the actual structure, to just that help me in parsing, deciding on what library type I'm dealing with. So now we move into structure number 3, which details the data members of type 1 library. So in this particular case, like this alpha image library, we're actually dealing with type 1 library. So take this as a perfect example for illustrating this particular library. So what should follow after 2, so remember, if type 1, 2 is constant, is the actual class name. And in this case, it is image. And then followed by number of referenced internal libraries. So in this case, we have 0, 1. This is the number of referenced internal libraries. So we only have one library. In this case, it's named image. What this means is that this library, this main library, alpha image, it's referencing the class image from a library under this name, image. So if you go into the directory pure libraries, you should find another library under the name image that exposes the class image. So how did I name them and make like sense of them in this way? It's just like by poking around and reading through the documentation and making sense out of it until the picture is clear. And now we go into type 2 library. It's not much difference from type 1, except that in type 2 library, the library might be referencing what I call system libraries. By system, I mean like if you're using a pure basic Windows version, as you recall in previous slides, is if you go into the Windows directory, you will see references to Windows libraries that the compiler calls into when compiling on Windows. So this here clearly say that if such system libraries are referenced, so they are in the header with their names. So if you're referencing, if this library references, let's say, something from adds API 32, you will see the name of the library here. And the rest is the same as type 1. Now, why the author makes such differentiation between the two, I'm not sure exactly, or why would he need to do that? I didn't go into do that much in depth of this, as it is irrelevant to my investigation. So that is that for this, for these couple of bytes. All right. So as I mentioned, those libraries, they are stored zlib compressed, either yes or no on Windows, whereas on macOS, they are stored encrypted, and they are not compressed at all in any form or shape. So how would I differentiate between the two when parsing them? That I'm dealing with a Windows or Linux or and macOS library. It turns out that the differences between the two headers is that the author sets in reverse order this data member, like instead of storing the decompressed size of the library, he sets it to the library version. So I do this exact check and see if this matches. This means I'm dealing with a macOS or Linux library and not Windows library. Initially, when I wrote the parser before figuring this out, I just let it to the user to decide. But turns out that is a way, like an easier way to do it automatically on behalf of the user. Now we go into an interesting set of bytes as well. It turns out that the author also stores in this proprietary file format what I call function declarations for all functions/APIs that this particular library exposes. Why? Again, I don't know why, because you could just reach out to the documentation, which has extensive like help for a given API, but he has them stored with some additional metadata. And there is a structure specific to this list of functions. So starting from where we left off, we see here we start with this end alpha image. So this is remember, this is the function declaration now. So first, this is the API name. By the way, there is no member, which is interesting. I don't know why the author decided to do that. Makes it even harder to parse. There is no like double word value that would indicate the number of function declarations that follows. So you have to do it on your own while parsing this, and meaning accounting for it the proper way. So, and alpha image is an API name referenced in this alpha image library. But again, it's nil terminated. This is how I know it is the end of the API name. And then we have this byte in blue, which should hold the number of arguments that this particular API takes. In this case, it takes 0 arguments. So what should follow is what's known as the argument list. And this list will hold the size of each of the arguments that this API takes. But in this case, this data member doesn't exist because this API doesn't take any arguments. Of course, it did not be the case just for this particular example that I'm illustrating. So what follows after that is what I call API type, and in this case, like it's a double word value, and it is highlighted here in green. And this actually changes for every API, for every library. And to be honest with you, I have no clue what it means, and it doesn't change anything from reversing perspective. It must have been used like for tracking purposes by the author. I just don't know why. And then what follows after this is an actual documentation, actually, like a full string documenting what this API does. But in this case, as you can see, we have 0. So it means this particular API comes with no documentation. And yeah, and you keep looping until you finish parsing the entire function declaration list. And they are stored in this very specific structure format. So done with the function declaration part, then we move into part 2 on the right. And this is the most important part, actually. This is the part that stores the, or I should say, that gives us all the information needed to pull the actual library in its plain format that we would use to generate IDA signatures. And it has the following structure. As the bytes in orange, you can see here, there's another header. There's another magic value. It's pure. It's stored in little endian. And then what follows is we have this another double word value, which stores the actual size of the library file as stored in the proprietary library. And then what follows after that is the type of the library that's stored. Is it a data library or a debug library? So it takes either of these values, DAT1 or debug1. Again, most of the data is stored in little engine. And what follows is the actual library content. And in this case here, you see it is starting with 789C. And this is actually how I tell that I'm dealing with a zlib compressed data, because this is the header of zlib compressed data. So you can simply actually just take the rest of the data all the way starting from this offset until the end of the library or until the end of the file, and zlib decompress on your own, should you choose to, without having to do all the rest of the parsing. But that wouldn't be an actual endeavor, I should say. That would be just cherry picking stuff. So if you recall, I mentioned that on macOS, those libraries are stored encrypted and not compressed. And this is actually pretty much the only time when I had to do, other than patching the PD compiler, where I had to do a bit of reversing just to figure out the decryption algorithm so that I can implement it in my parser. And the decryption algorithm is actually quite simple, extremely simple actually. And it has this key of double word value, which is constant for all versions that I was able to gather and look into. And for decryption, it's just simple. You just take a double word value at a time, and you subtract it from the key, and then on every iteration, you add the file size, meaning the data member here, the length, to the key, and you keep repeating, and you get the decrypted stored library. It is as simple as that. Now, okay, so we're done with the parsing of the proprietary library file format and extracting the actual library we're interested in. Now we come to what's known as a resident files. As I mentioned, these resident files, do not confuse them with resource files. These are specific to Pure Basic. They have this structure. So as I mentioned, these resident files, they contain macros, interfaces, meaning classes, constant values, or whatnot. They are stored in binary format, and they have and they follow this structure. I didn't find a need to add this feature to my parser, but I'm just stating here in this slide just for reference purpose should anyone else decide to parse these by themselves. And you might be wondering, like, how did I figure out that, for example, let me say, like, for example, here, prod. I have this this unique marker called prod. Like, how do I know that this implies that that the payload that follows this marker is where the interfaces are stored? Because you didn't do any reversing. It's just a matter of looking at this stuff and making sense out of it. Like, what is the name of this? And then go check the help file and look at it like this. You literally don't have to do any actual reversing. Now, so this is just like some general notes from this experience on what you should consider while reverse engineering proprietary file format without doing any actual reverse engineering. And I believe I've already stated most of this stuff, but just to reiterate, whatever framework you're reversing, you got to familiarize yourself with it. Irrespective of how complex it is or what technology it is using, you're going to have to read into it and read documentations, poke in every directory, and execute this, execute that. And whenever you're in doubt, just Google it and see if somebody else answered some of your peculiar questions that you can't answer yourself. And of course, the most important part in all of this is the hex editor, whatever hex editor you use. And experience does indeed play a major role when like trying to reverse engineer such stuff without actually doing any reverse engineering. because it helps in identifying certain patterns and specific constructs that you otherwise wouldn't be able to do easily. You can, but not easily. You would have to get a gray hair until you get it right. So just to make this note clear, reversing binary format is definitely different and more difficult. Not only from reversing perspective, even from parsing perspective, especially when you're dealing with dynamic data, with data that you don't know the size of it, it makes parsing really, really hard compared to reversing text-based format such as HTTP protocol. Although parsing HTTP is not also that simple, but nonetheless, it's quite obvious what you can do with HTTP. You don't need to second guess things. So just like just some general recommendation when reversing binary format is the first thing that you need to account for is to look for string that ends with the delimiter, the null terminator character, and you have to make sense of types of size 1, of size 2, of size 4, depending on the architecture you're dealing with, and not the endianness, whether you're dealing with little endianness or big endianness or whatnot. And again, you need not keep focusing on the first byte or first 16 bytes when you're reversing like a file of 20K bytes, for example. No, you're going to have to go through it first, or at least not first, a couple of times, to look at the entire thing in its entirety, trying to make sense out of it so that you don't lose concentration just by trying to make sense out of this one particular byte. What does it mean in the context of this entire thing? So yeah. So after doing all of this, and I ended up writing parser, my own parser, but you could use Kaitai with its own high-level language to write a parser for it. Although I don't know how would you do it in an easy way. There's a learning curve to it. Or you could use a Blobify. It's a C++ 17 compatible library that allows you to parse like serialize, deserialize data. But again, it's also not up to the par of what you would want to achieve. It would require a lot of work to do the same thing. So I would actually suggest that you write your own parser instead and take it as a learning experience. So I wrote it in C++ and it parses all the libraries for all the platforms, and it gives you all of this fancy information from what we saw in all of the documented structures. And it can, of course, extract the library to disk and or the function declaration in XML5. So to give you an example, there is nothing fancy about it as much as just to prove that it does exist and it works. So first you give it the library. In this case, I just took as an example the gadget library. And if you want to print to the console all these fancy structures in a contextual manner, so just give it the P option. It prints everything to you, including the function declaration and whatnot. But here I'm just gonna outline some stuff. So this is all the stuff. And what I want to show you is, for example, this particular library is a type 2 library. And you can see it here, like the reference system libraries. So these are the names of the reference system libraries. In this case, it's Windows, and it's referencing these Windows libraries. This is what I mean by system function declarations. As you can see, this particular library has this huge list of APIs stored in it. So first you have the API name, number of arguments, and then followed by the size of each of the arguments. Yeah, you would be surprised to know that there is some of the arguments hold the size of 40 bytes. If you check the documentation, you will see why. And then the type, as you can see, the type is double or value and changes per API. I have no idea why. And then followed by the like help that describe what this API does. What else? I mean, you can extract it, just an E, and you get the library. It generates the gadget.lit for you. You wanna dump function declaration to an XML file. It generates the XML file for you. And let me see how it looks like. All right, gadget. Hopefully we'll get so this is the list of function declarations in XML format. Should you decide to consume them in one way or another, so they are stored in standardized format. For the library, if I get to the directory this way. Yes. So this is the extracted library. So if you open it with your hex editor, see it. As you can see, this is cost stuff and extracted as well. So now going back to the slides. Again, so to make reversing this even more easier, I wrote an IDA-Pro plugin. It's written in C++, and it allows you to check if the binary loaded in IDA is a pure basic binary or not by checking for certain prolog functions. Again, this is all specific to Windows, so I can just work on this for like endlessly and accounting for the Linux and macOS version. Hopefully somebody else will pick it from there and add the rest of the functionalities. And of course, I generate IDA flirt signatures for all the libraries for the Windows version of the compiler. And depending on whether you're dealing with 32 or 64-bit, the plugin will automatically apply their respective flirt signatures, so you don't have to do anything. And after applying those signatures and then the code becomes clearer, you can look up any of those APIs just by right-clicking on it, and either by going straight to the online documentation, or you can move to the CHM help file into the plugin directory and open it from there. It takes you straight to the API. It's a very simple plugin, but it just automates some of the steps for you, so you don't have to wander around. And in case you're wondering how the plugin identifies that we're dealing with a pure basic or not, like this is, for example, for detecting 32-bit executables, it checks for this particular assembly code snippet, which is actually the prologue of every generated pure basic executable on Windows. And this is literally how I have this array stored in the code with these wildcards as well. And if you reverse on your pbcomposite.exe file, you will see exactly these assembly instructions being emitted to purebasic.asm file down to the constant. And if you want to like DLL 32-bit, it has this prologue. I'm not gonna do too much. Not gonna talk too much into these. If you want to detect 64-bit, this is how I check for that. Now for generating IDA flirt signature, I'm not sure if you're familiar with it or not. I mean, it's not a rocket science. You already have all the tools when you download IDA SDK, and so yeah, I really don't know if I should. I'm not sure if I'm already over time or not. Am I over time, Matt? Okay, awesome. Okay, gotcha. Okay, so for generating a flirt signature on for any of these libraries that we gathered, first you use this tool called pcf.exe, which is the cost parser, and for other file format parsers, also IDA SDK does come with other parsers, but in this case we're dealing with cost file format type libraries, so we use pcf.exe, and of course you have binaries for each platform. These are all included in the SDK, and this would give us the actual library pattern file that we would use to generate the final signature. IDA has great documentation of what these pattern files entail, like down to the specifics. So once you generate that pattern file, you use sigmake, which generate the actual final signature file. And of course, it's an iterative process from this point on, because you might encounter some collision, especially if you have functions with like a few bytes. So those you might have to fix manually, and it's quite easy. I already did that for those I shipped with the plugin. So you didn't have to worry about any of those stuff. But nonetheless, those collisions, they actually, they're really not that important because they deal with functions of debug nature. So they don't touch on the actual functionality of a given API that you're sort of afraid of missing on, that the flirt file did not auto identify for you. So yeah, that's all. It's literally quite easy to generate those essentially. However, just keep in mind that you have to have a paid version of IDA to generate those signature files, because the SDK is not free. So as a case study, just to make sure that this thing actually works. So actually, I didn't mention this at the beginning, like the trigger behind this project. My first encounter with the Pure Basic was in 2015. I looked at a malware at that point in time, but I didn't write about it or anything like that, just internal work. And I didn't do much work on Pure Basic. I got done with that reversing, and that's it. And now fast forward to 2019 in November, Integer published blog post on what's called Pure Local Ransomware, and it was written in Pure Basic, and that's what got me interested again in Pure Basic and to do all of this work. And so this ransomware is written in Pure Basic, and I just don't know what version of Pure Basic, and it uses some custom functions and time analysis and whatnot. So originally, when you load it in IDA, you get only 18 out of 231 functions identified. But after applying those IDA flirt signatures, you will see that 124 were auto-labeled for you out of 237. And you can see that an additional 6 functions were discovered. No wonder, since IDA has more information now. So just to give you like 2 screenshots about the difference between the original non-labeled DB versus the labeled one. So well, actually this shows the labeled one. So as you can see, like this is how Pure Basic API names look like. It's already labeled these for you, and so they are self-explanatory. And if you're dealing with a ransomware, you can see the call to these encryption algorithm functions. So you don't have to peer into every function just to figure out what encryption algorithm the ransomware is using, whatnot. It's already stated for you in the function name. And another example, this is just like I took it from the examples directory from Pure Basic. It's an XML file that does all it does, it uses the XML library. It loads an XML file from disk, and it parses it and displays it in a GUI dialog box, type dialog box. Originally, I identifies only 41 out of 555 functions. After applying the signatures, you get 300 out of 585. And as you can see, I also discovers a new 24 functions. And to see the difference, originally, as you can tell, you have no clue what this particular binary is doing. After applying the signature, after flirting it, you can see now it makes much more sense. You already know what it's doing. I mean, this is personal experience, so these might not be challenges for you. But the challenge I myself encountered is getting a hold of all of these versions of Pure Basic compiler, because on the Offshore website, they also only list the most recent version. And getting access to those old versions just to generate the required flirt signature for all of them, you don't need to account for the minor releases, at least the major one. It's really hard. And even if you go on VirusTotal, it's still hard to find them. So I don't know how would you find all these prior versions. I'm pretty sure somebody else might have stored them somewhere. Yes, what is left is generating their signatures for Linux and macOS. This is literally just from now on, it's just a manual work. Somebody has to do it. And probably update the parser to parse the resident files. And probably add to the plugin the capability to load the function declarations and annotate all the identified functions, although I don't see this to be an important feature. But what's important is adding the identification for pure basic macOS or Linux binaries, and for dealing with those unidentified pure basic functions or those missed on collisions, perhaps we can use IDA to path plugin and do this like the manual way and generate another set of third signatures that deal only with these unique unidentified functions. So they are shipped under a separate signature file. This is more of a recommendation for anyone who tries to write their own parsers when parsing binary files with dynamic offset, dynamic lengths, with missing or not missing, just from design perspective, the author doesn't mention the length of what follows, and you don't know where to end when you parse stuff, is that it's always, at least this is my own learning experience, that if you know what this structure holds in terms of all the data members that you have to account for, just take that blob into a separate buffer and parse it separately. Because you can have a hard time accounting for all of these offsets, especially when you want to display it out. Because in my parser, I display out all the offsets like correctly, the proper way. Other than that, it's literally just a trial and error type endeavor. So you're gonna have to try this, try that until things start to make sense for you. Perhaps I can show the plugin. It should be quite fast. So here, for like this is the XML file that I showed. So this is initially loaded here without either third signatures. So if you go right-click, Kuba helper. First, we ask it if it is pure basic binary or not. It says it is a pure basic binary file. Do you want to apply third signatures? Say yes. And then it asks you what type of libraries do you want. I mean, by default, you have these first two selected for you, since yeah, the most common ones. But if you know you're dealing with DirectX or OpenGL, you can just select them. It doesn't, I mean, hurt to select them too. And then if you click apply, and then you can see that the plugin already auto-identified this stuff for you automatically. And just to make it even nicer, you can make it even this way. So as you can tell now, the code is much easier to read. So all the functions are labeled for you now. And for the case of pure locker, it's also the same process. Is it PDF file? So you say yes. And if you go here, you can see these sys underscore, pb underscore, all these labeled functions for you. So yeah. So yeah, that's it. And conclusion. I don't give conclusion actually. I leave it to the reader to make up their own conclusions to see if they understood the presentation or not. And at the end, well, thank you for listening. And I'm sorry again about the hectic beginning with all these technical errors. Thank you.
It's okay. It happens. Thanks for your presentation, and we'll post it on YouTube, and on the YouTube version, I will cut like the technical like issues, so it should be like a bunch cleaner. But it's interesting because I don't know which phone you're using, but the quality is pretty good actually with the microphone. Not with
should I say the name or no?
Not the microphone, but the actual like phone or cell phone you're using. I mean, the sound is pretty good.
Oh, awesome! That's good to know.
Yeah, it's a good backup plan, if you ever have any issues.
Okay,
So
it's a OnePlus phone, just for the record.
okay. Oh, it's from a cell phone, huh?
Yeah.
Okay, interesting. Questions from the chat. Will you share the Flirt signatures that you generated?
Yes, I do. The Flirt signature, the parser, and the IDA plugin, and the
Very
slides.
cool. Very cool. And is it another Packer advanced model? Question mark.
Pardon, what is that?
Is this another Packer's advanced model?
It's not a packer at all. This is a compiler. It's got nothing to do with a packing or anything like that.
Because that guy also oh yeah, it was a bit unclear about what you were trying to do. Like I'm reading the initial messages like, oh, it seems Trend Micro analyze techniques used by hackers in the wild, pairs of speakers talking about compiling PB to ASM. I'm not sure. Yeah, that makes sense. Cool. And have you ever seen like a malware using Pure Basic?
Yes. So for here, actually, surprisingly, on April 2nd, again, Avast actually published a blog about a malware with the installer written actually Pure Basic. And then you have Pure Locker. And then you have the one I encountered in 2015. And then after I did that, actually, I wrote a threat hunting rules, Jira rules on VT. And then once you run those through, you will see how many malware written in Pure Basic. There's a lot.
Oh, you mean like the rule you were showing before? You used it in VT, and you're getting some samples now, so you're still looking at them.
Exactly. Yeah, because now I am able to fingerprint the Pure Basic binaries, and then I add some specific check just to give me an indication whether I'm dealing with a malicious Pure Basic binary or not. Yes, you will get to see a lot actually.
Yeah, that would make sense. It kind of reminds me like back in the days, when people were writing like crackmes in Delphi. When people had to like disassemble them and to look at them, they were like going like, oh, like what is this? Because of P code and everything. So Pure Basic. Actually, it's the first time I hear about Pure Basic. I didn't know at all about Pure Basic. So it would be quite interesting if you can find a bunch of them, maybe from the same authors, or like same group of authors.
Exactly.
Yeah.
Yeah,
That's
cool.
cool.
I wouldn't be surprised because it's a cross-platform. So
yeah, I guess instead of like other languages, especially if like you said cross-platform, like even like now, like usually we don't see that many like Linux malwares. So if there's some Pure Basic malwares running on Linux, that would be like quite interesting to watch actually, because even for like regular binaries on Linux, there's like almost no one analyzing malwares. Windows, there's a lot of people. Mac OS, there's some people. Linux is like, it's almost like dead no man's zone, like as if it does not exist, but we all know there is plenty of stuff.
I agree. And usually nowadays they are focusing on targeting IoT devices. Like you get to see a lot of Mirai variants and with additional functionality like this Linux-wise. It may not be Linux specific, but this is what the major focus now on the Linux side. And for Linux, I mean, based on my, it's my work is mostly like whenever like an advanced persistent actor wants to target particular organizations, then they write, of course, Linux, Mac OS, or Windows binaries. So they still not as widespread as Windows, as you mentioned.
Yeah, I don't know if they're less widespread. I mean, definitely, but they're more targeted because, like cloud, if you just look at cloud operating system, more than 50% of them, like even on Azure, is Linux. And if you have like some Linux OS, on any like cloud providers, well, that's basically to us like your servers, right? So it's gonna have valuable information for sure. Whereas like Windows, there's a lot of desktop and everything, so it's kind of like a different landscape. Which is a bit of a shame because like if you look at cloud security for like malware, so especially for Linux, it's just very bad.
Exactly, and I totally agree. I think it's just a matter of time before the attacks start to catch up with the current landscape, like in terms of cloud Linux adaptation. And I think Sophos like recently published a paper about an actual incident targeting cloud services where a Linux malware was used.
I think Intezer also like published some stuff like a few months back. Even internally, like we're very like because we have a platform for memory analysis, we're like really focused on Windows for a while, and last year we kind of like started to pivot to focus more a bit on Linux, just because of like Cloud OS. There's a huge gap there, and like no one knows how to do anything, you know. Because like and Windows like knowledge like really varies. Like you're gonna have some people who are gonna be like really good, but a lot of the people like are gonna be like really average for Windows like analysis, and it's always like the same thing for malwares. So it's kind of like difficult to like even if you look at like malware trainings, you know, they're kind of like all a bit of the same. You know, it's very basic. So that's really interesting to see if there is more like pure basic stuff. Have you seen like many people doing research on pure basic before you started to look at it, or is it something like?
No, I'm actually the only one. There is no prior research in this area. I tried my Google Kung Fu skills to see if somebody else did any research, but none actually.
Yeah, I mean that. And how did you find the first like pure basic sample, the one you were looking at?
Oh, back in 2015.
Oh, it was in 2015 now? Oh, wow.
2015, yeah, I know. And I still have the report.
I needed the research only now?
Only now, exactly. It's only now. And I didn't pay attention at all at the beginning, like back in 2015. I actually didn't have time, to be honest with you as well. It's only now that I got so interested again in this. And I've become wiser and more experienced. So
yeah, it definitely plays with it. Yeah. And it's a commercial language, right? Or is it open source?
No, it is commercial, but it's quite cheap actually. It's and the license is perpetual.
Okay.
It's very, very, very cheap.
Yeah, that's yeah, I'm just checking on internet now actually to kind of see.
Yeah, it is purebasic.com.
What type of people use it like generally? Because it looks like very obscure.
I know it's used for writing games, databases, editors.
Oh. Yeah. Is it like a legacy like programming language or?
Actually, it does inherit as per the author's history of the language. He does clearly mention that it tends something from the basic language itself.
Okay.
Like in terms of like a syntax and whatnot.
That's that's pretty cool. Well, let me check if there is more questions in the chat. I don't think so. All the slides and stuff will be available on GitHub. Mohamad, I'll send you a link. Also, like I uploaded your slides already, but you know, like all those references, you know, like for like the float signature, your IDA plugin and everything. Don't hesitate to add them to the README for the GitHub. So like there is also like the other references. So it makes it like quite easy for people to kind of like look at all the information. And yeah, that's pretty much it. Well, thanks again to you, and pleasure to have you with us on Upcode. And yeah.
Well, thanks a lot for giving me the opportunity to present this work.
No worries. I know it's a tough time to find a place to present like stuff now because of the thing. But you know, definitely that's really cool research. And actually, I was surprised when I saw your slides because like there's so many. I was like, oh wow, actually you did like a proper like presentation and everything. I was like, okay, cool, you know. Because usually the format is 30 minutes. I was like, oh, this guy actually did like some proper work. So like, I'm definitely going to give him an exception.
Oh, yeah. I was actually worried about that, like timing wise.
Yeah, no, it's okay. Okay, well, thanks again. Have a nice day.
Thanks, you too. Bye.
Bye.